Hello everyone. So today we're going to be continuing with the overall topic of vectors, and specifically we're going to be talking about velocity and about navigation, bearing, and heading. So basically we're going to be talking about an application of vectors. In other words, a way in which vectors can be used. So let's start out by talking about the concept of velocity. So velocity you can kind of think of as speed. So like a car might typically go at a speed of 60 miles per hour, right? But velocity goes a little further than that. Velocity is a vector, so it also indicates the direction of travel. So for example, let's say we're looking down at a city from above, and let's say here's a car here. We might say, okay, its velocity vector is like this. And so its speed, we would say, is the magnitude of the vector. Let's just say 60 miles per hour. But then that vector shows the direction it's moving, right? So maybe, if we're using the normal compass directions, we would say this car is going 60 miles per hour due east, as in straight east. But then let's say there's another car over here. And maybe this one's traveling north at a slower speed. So then maybe it's that car's velocity vector goes like this, a little shorter than the other one, and maybe its speed is 45 miles per hour. So again, we would say this car's velocity vector is one that's pointing straight north with magnitude 45 miles per hour. Now let's talk about how velocity vectors can combine. And we've kind of talked about this in previous lessons, but let's go into a little further detail. So here we've got three diagrams of the same plane. And let's say with no wind, this plane would be going forward at 190 miles per hour. So it's velocity vector 190 miles per hour, right? Same in all three examples. But let's say in the first example, there's a wind that's blowing in the same direction as the plane's direction of travel. So then we might say, okay, the wind combines with the original velocity of the airplane, like so. And let's say the wind is blowing at 20 miles per hour. So what happens then is the wind combines with the airplane's original velocity and makes it go faster, right? So the total velocity of the airplane relative to someone from the ground, relative to an observer on the ground, the total velocity here would then be 210 miles per hour, right? 210 miles per hour. However, what if the wind is blowing directly opposite the direction of travel? Then the wind would sort of provide resistance against the airplane's movement. So like this, for example. Again, let's say it's 20 miles per hour. So then the total speed of the airplane would end up being 170 miles per hour in this case. By the way, the first example, we would say the wind is a tailwind. The second example, just now, we would say the wind is a headwind. And then now let's look at an example of a crosswind. So maybe the wind is blowing this way, perpendicular to the movement. And in this case, 20 again, in this case, the total velocity vector of the airplane would look something like this. And we would have to calculate the speed, the magnitude there. But notice how it would sort of veer off to the side. And that would be called a crosswind. Also notice that the magnitude, the length of that vector would be a little bit longer than 190, right? So this crosswind might cause the airplane to go a little bit faster in terms of total speed, as in terms of magnitude, but it would still be going a little bit off to the side. So we're going to start doing problems where we're calculating velocities and such, right? But before we do, we have to talk about two different systems we use to describe angles. Because we have a way of describing angles, direction angles so far, right? You know, in the same way that you might have learned in a previous math course. So what we've been doing so far. But then there's this other way of naming the same angles, and we call that like compass headings, compass bearings. So let's compare those two systems. Let's use the example of 150 degrees. And so far, we've always said 0 degrees is here, right, in the positive x direction. And then 150 degrees would be like this. Because we start at 0 and go counterclockwise, right? 150 degrees going counterclockwise. But then that same angle, when we describe it as a compass heading or bearing, we give it a different name. So the angle is still the same on our diagram, but then with a compass bearing, we're going to be saying how many degrees it is relative to north. And then here would be east, south, west. So we say north is 0 degrees, and then we go clockwise. So starting with this being 0 degrees, we would go the other way, this way, to get to the same angle, that terminal side of the angle, right? And so in our problems, you're going to need to convert between the angles we've been using so far and those same angles as headings or bearings. We're going to need to convert back and forth. So how do you do that? You know, first of all, I would always recommend sketching it out. And then you kind of have to use your diagrams and figure out some of the angles in your diagram to help you out. So for example, our 150 degrees under our previous system, we start at 0 and go counterclockwise, and to get here, that's 90, right? So then to go the rest of the way, that's 150 minus 90, so this right here is 60 degrees. And then if we go backwards, this is 180 degrees. So then this little angle here is 30 degrees, right? And now those angles that we've marked will be the same on the other diagram. So 60 degrees right here, 30 degrees right here. And we can use those smaller angles to figure out what this angle is as a compass bearing. So again, we start at 0 and we go clockwise. So 0, this would be 90 degrees. This would be 180 degrees. 270 degrees to get due west. But then we go 30 degrees further from 270. So 270 plus 30. And how many degrees is that? So that's 300 degrees, you know, relative from north going clockwise, and that's the compass bearing version of our 150 degrees. You could also say if we're starting at north, if we went all the way around, that would be 360, and then going backwards 60, that would give us 300 degrees again. So that's two different ways of thinking about it. So again, the same angle, 150 degrees as we would have labeled it before, but 300 degrees as a compass bearing. Even though on our diagrams, they're in the same location. So another quick example, let's say we're working with a bearing of 190 degrees. So here's north. Where would 190 degrees be? So north is 0, going clockwise, we go 90, 180, and then 190 would be just a little bit further here, right? That's a little bit too big, but you get the idea. 190 degrees. So then under our normal system, our previous system, we'd have the same angle here. But then how would we get to that same place starting from 0 over here and going counterclockwise? So by the way, note that if this is 180 plus a little bit more, that little bit more is 10 degrees, right? So then this will be 10 degrees. And then this right here will be 80 degrees. So then starting at 0 going counterclockwise, we have 90, 180 plus 80, that would be 260 degrees. Again, bearing of 190 degrees, that's 260 degrees under our previous system. By the way, problems will refer to common directions without attaching a number to them. So let's go over what their numbers are, both in terms of bearings and in terms of our normal direction angles, okay? So we've got due north, so straight north, due east, due south, due west, and then we've also got directions like northeast. And even though my drawing isn't like very straight, we're assuming that this is exactly in the middle between north and east. Then of course we've got southeast, southwest, and northwest. So first, let's go over what the bearings of each of these directions are. Bearings, we start at north as 0 degrees and we go clockwise. So northeast is 45 degrees, due east is 90 degrees, southeast is 135 degrees, and so on. 180, 225, 270, 315, and then back all the way around for 360. And that's bearings, right, with 0 at north. And then in terms of our previous system, the normal mathematics way of describing angles, we've got east is 0 degrees, due east, and then going counterclockwise, northeast would be 45 degrees, north would be 90, northwest 135, and so on. 180, 225, 270, 315, and then back all the way around. So again, the blue is the bearings, the red is what those equivalent angles are under our previous way, under the normal mathematics way of describing direction angles. Okay, so here's a straightforward example. An airplane is flying on a bearing of 165 degrees at 460 miles per hour. Sketch the velocity vector, name its direction angle, as in like normal math, and write the vector in component form. So they're giving us a bearing. Basically, we're converting from a bearing to what we've been doing with vectors. So let's sketch it. Let's see. Now, pay attention. What they're giving us is a bearing of 165 degrees. So that means we start at north. And then 165 degrees, we're starting at 0 and going clockwise, so 90, but not all the way to 180. So something like this, right? So between east and south. And then its speed is 460 miles per hour. So take note that that's the magnitude of the vector. And really the key, first and foremost, is to convert the bearing of 165 degrees to our normal type of direction angle. And then once we find that angle under our normal system, then we've got this formula from before, right? That you can use the magnitude and the angle with to find the component form real easy. So let's see. We've got the bearing, but now from 0 degrees here under our normal system, we go counterclockwise, 0, 90, 270. But then notice that 165 from north would mean there's how many degrees here? From north, south would be 180, so there's 15 degrees, 180 minus 165. And then under our normal system, 90, 180, 270 plus a further 15 degrees, that would be our direction angle is 285 degrees. And that's that theta in our formula, right? Theta is 285 degrees. And now that we've found this key angle here, we can just apply the formula. So let's see. So this V in absolute value symbols, that's the magnitude, is 460 times cosine of the angle we found. Not the bearing, but the ordinary angle, right? Comma 460 times sine of 285 degrees. Stick this in your calculator and you should get that the velocity vector is around positive 119.057 and negative 444.326. So that right there is the component form of the vector in the terms that we've been dealing with vectors, right? Does that make sense? So our diagram, it goes from the origin, we would go right and then down. And then our answer here, positive would be going right, negative vertical component would be going down. So yes, there it is. Okay, so now we got a more complicated example. It says, suppose an airplane is flying on a compass bearing of 310 degrees and its speed would be 520 miles per hour if there was no wind. So that's like the original velocity of the airplane. But find the airplane's actual ground speed and bearing if there is a wind that is blowing due east at 66 miles per hour. So first, let's just sketch the situation. The airplane is flying on a compass bearing of 310 degrees. So starting at north, going clockwise, 310 is somewhere around here. And then the magnitude is 520, right? But then the wind is blowing. So remember, this means that the vectors are combining, right? So the wind is blowing due east. Due east is to the right, but combining with the vector, the original velocity of the airplane, so like this, let's say, is the wind. The magnitude there is 66. And then the total velocity, if you remember how vectors combine graphically, right? Start at the origin, first vector, second vector, start at the origin and go to the head of the second vector. So that is the combined result, the vector sum of the original velocity of the airplane and the wind. And it says find the airplane's actual ground speed and bearing. That means, okay, the total result, we have to find the speed as in the magnitude of that, and also its bearing as in its direction from relative to north, right? And for this problem, what you have to notice is they're giving us vectors in terms of bearings, right? So the airplane's velocity they're giving us as a bearing, same with the wind. And then we need to figure out this total vector, but we're giving that as a bearing. But unfortunately, when you do calculations with vectors, you want it in terms of the other system of angles. You want to be working with our normal math direction angles, right? So what's going on is we need to take the vectors in terms of bearings, the two that we're adding, convert them to normal direction angles, and then we can add them. And after we add them, then we need to convert the final product back to bearings. So this is going to be a lot of work. So let's take it step by step. First, let's start with the airplane's velocity vector, right? And we're going to convert it to a normal direction angle. So airplane velocity, like what its propellers are doing without the wind, right? And we said 310, and it's around here. So again, look at the diagram, figure out what angle that would be in terms of our normal direction angle. There's 50 degrees. If this is 310, then there's 50 degrees here. So then starting from 0 degrees here, that would be a total of 90 plus 50. So in terms of our normal direction vectors, direction angles, this thing has an angle of theta equals 140 degrees. And now we can find the component form of that, right? It is magnitude's 520, times cosine 140 degrees, comma 520 sine 140 degrees. So the component form of the airplane velocity is around negative 398.343, comma 334.250 if we round. And does that make sense? Is it going left and up, negative horizontal component, vertical, positive vertical component? Yeah, that makes sense. So actually, let's move that over here. But now we have to do the same for the wind velocity, right? So what is the wind doing? So it's going due east, this direction, and the magnitude is 66. Now you could use that formula. You could do 66, and then that's the bearing due east. But how many degrees is that in terms of our normal direction angles? That's actually exactly 0 degrees, right? It is pointing in the direction of 0. So you do cosine 0 degrees, comma, 66, sine 0 degrees, and you will find that the vector is exactly 66, comma 0. That makes sense if you think about it, because this vector is totally horizontal, right? So all of it's going in the x direction, and 0 for your vertical component. It's not going up or down. So now we've got the airplane velocity in component form. We got the wind velocity in component form. So we can find the net velocity, the total velocity, by adding them, right? Because we know how to add vectors in component form. So the total velocity, how do we add vectors? We just add corresponding components, right? So horizontal component, that's negative 398.343 plus positive 66. So around negative 332.343. And then for the vertical component, 333.250 plus 0. So we just keep the vertical component from the airplane velocity. And so this right here should be the total result, right? The component form of the total velocity vector. So that's good, but note that that's not what they're asking. They're asking the ground speed and bearing. So let's sketch just this total vector. And by the way, notice that the component form that we found checks out with our previous sketch, right? The total vector should be going left and up. So anyway, let's just sketch this alone. Left and up. And now again, it's asking for the speed and the bearing. Remember that we can find the speed, as in the magnitude, easy with a formula, right? Just Pythagorean theorem. So it goes left negative 332 point something, and then above 334 point something. The magnitude here, x squared, is around negative 332 point something squared. In your calculator, you should have more digits than that. Plus 334 point something squared. So find that in your calculator, square root both sides, and you'll get that the magnitude is around 471.354. And this is like a real world or physical setting, so don't forget, what are the units? It's miles per hour, right? And that's our actual ground speed of the plane. So now what about the bearing? Well, we can use our normal methods to find a normal direction angle and then convert that to a bearing. So the direction angle is this angle, right? But what we say is, well, we've got a right triangle here, so we can also think about finding the angle here. and you'll see, okay, this side is opposite, this side is adjacent. So we can be like tan of these angles is this 334 thing, point, when you're actually doing it, keep more digits, divided by this negative 332 thing. And then you take the inverse tan of both sides to get around negative 45.164. And you know, that's weird because that angle is down here, right? Where's negative 45 from 0? That's like this angle. So these vectors and finding direction angle can turn out weird and messy like this. If that confuses you, just use the right triangle and use positive lengths, and you will find that this angle in here you can think of also as being positive 45.164, right? Just dealing with it as a triangle, you'll find this angle is 45.164. So in any case, the total effect of it is the actual angle for this vector is 180 minus this 45 part. And you'll get that the angle is around 134.836 degrees. And you know, that checks out with our diagram, that's good. But again, that is a normal direction angle, and we're being asked what the bearing is. So our diagram's gotten kind of messy. Let's draw yet another separate diagram. So here's our vector again. We just found that this part is around 134 point something. Actually, this will help as well. We also found that this is around 45 point something, right? So then to convert to a bearing, we say, okay, north is here. Starting at 0 degrees north and going clockwise, we go 90, 180, 270, and then we go a little bit more to get to our vector, right? So actually, yeah, that 45 does help because it's 90, 180, 270 plus that 45 part. And so as a bearing, we get around 270 plus that 45 part is 315.164 degrees approximately. So there it is. That's what we were looking for. So to summarize, we were given the airplane's velocity without wind plus the wind velocity. We converted those to component form to find the total velocity in component form. And then we used our normal methods to find the length as in the magnitude, our normal methods to find the normal direction angle. And then we took that direction angle and converted it to a bearing, and that's what we were asked for. So again, there's a lot going on. If you run into any issues, as usual, please feel free to contact me with questions or feedback.